Homogeneous systems. Let's talk about how we can find the basis for the solution space W of a homogeneous system. So here is a homogeneous system, and we want to find the basis for the solution space. Let's try this one. Okay, so we multiply this. Well, since there are 1, 2, 3, 4, 5 columns, I multiply by x1 through x5. Because remember, this row has to be dotted with this column. They have to have the same number of entries. So we want to find the solutions, a basis for the solution space. Now, why did I put 5 zeros? Because the first row is dotted with the first column, and the answer goes there. And the second row gets dotted with the first column, and the answer goes there. And eventually, the fifth row gets dotted with that column, and the answer goes there. 5 answers. But how do you solve this? How do you find the basis for the solution set? Well, you take this augmented matrix, and you write it down first. You take this augmented matrix, and you got it. You reduce it. And it reduces to the following. 1 and then 4 zeros, 0, 1 and 4 zeros, 2, 2 and then 3 zeros, 0, 0, 1, 0, 0, and lastly 1, negative 1, 2, 0, 0. And of course, since it's a homogeneous system, the right-hand side will never change. So you reduce this matrix, you get this, you get a row equivalent matrix in reduced row echelon form. And here it is. The first row has a leading row. The second row has a leading one, I meant to say. The third row has a leading one. And the columns were labeled by that vector. x1, x2, x3, x4, and x5. x1 has x1 column, or column x1 has a leading 1. Column x2 has a leading 1. x3 does not. x4 does. There it is, 1. And x5 does not. That means x3 and x5 can be any entry. Now, the first line says, first row says 1x1 plus 0x2, which I won't write down, plus 2x3 plus no x4s, plus 1x5 is equal to 0. The second line says 1x2 plus 2x3 minus 1x5 is equal to 0. The third row says x4 plus 2x5 is equal to 0. And the fourth row, okay, so 1, 2, 3, the fourth row says that okay, and we know that x3 is r, some real number, any real number, and x5 is the real number s. So if I may, I'll put the answers here. In this first equation right here, if you bring those terms over that, if you solve for x1, x1 is negative 2x3, but x3 is r, plus 1x5. That is plus x5, which is s. And x2, bring the x3 and x5 term over. You get negative 2x3, but x3 is r, plus x5, which is s. And the third equation tells us, okay, so just to go in order, x3 is r, and the next equation, x4, is bringing the 2x5 to the other side, becomes negative 2x5, that x5 is s. Like I said, x5 is s. So that is the solution space. All the vectors have to be in that form. You get to pick any r and s that you like, and you will have a solution. Meaning, when you take this matrix and you put in the appropriate x1 through x5, maybe let r be 2 and s be negative 7. So whatever you get, x1, x2, whatever you get, you plug in here. You will get 0. Just plug in any number you like for r and s. But you have to do the same r and the same s for all 5. x1 through x5, they get the same r and the same s. And you will have a solution. But the problem asks for a basis for this solution. The problem asks for a basis for the solution space, which they're calling W. The set of solutions is called W. Now, when I look here, when I look at x1 through x5, I see r's and s's. x1 is negative 2r plus 1s. x sub 2 is negative 2r plus 1s. I don't know if I wrote it down wrong earlier or not, but it's actually minus s. It's actually minus s. Sorry for the typo. Okay, and x sub 3, well, that's r, 1r, plus no s. And x sub 4 is just negative 2 s's. That is, it's no r minus 2 s's. And x5 also has no r's, but it has 1s. Now, this whole mess is equal to, I can factor out the r, and I will have r times those numbers, plus I factor out an s times that vector. Times that vector. That is, r gets multiplied by negative 2, negative 2, 1, 0, 0. Those numbers. Plus, I factor out an s, and then I multiply by those numbers. Negative 1, 1, 0, 2, 1. Every vector in the solution space can be written like this. Every vector in the solution space can be written like this. If I let r be 4 and s be 1, then one solution will be negative 8 minus 1, which is negative 9. Negative 8 again, plus 1 is negative 8. 1 plus 0 is 1. Sorry, 4 times 1 is 4, plus 0. 1 times 0. 4 times 0 is 0. 1 times 2 is 2. Add them up, get 2. 4 times 0 is 0. Plus 1 times 1 is 1. 0 plus 1 is 1. That right here is one of the vectors in the solution space. It's one of the solutions. Okay. Since I wrote on this as much as I did, let's get rid of it. So we need to look at the answer, the result that I just erased more carefully, because it is screaming the answers. It is screaming the answer quite loudly. Every vector in the solution, every solution to that homogeneous system of equations is in this form. It's a multiple of this vector plus any multiple of that vector. It's any multiple of this plus any multiple of that. Well, isn't that exactly what the span of this set is? The span of just those two vectors. I need more space, lovely. Isn't this right here the same as the span of those two vectors at the bottom right? Let me write down what I'm talking about. Now keep in mind that what I circled in the bottom right, R and S, can be any real number. But isn't that the span of these two vectors? Isn't this and that exactly the same? The answer is yes. Every vector in the span of this is in the solution. Every vector in the solution is in that span. And they're calling the basis, they're letting W equal the solution space. So the basis for the solution space is just those two vectors. -2, -2, 1, 0, 0. And -1, 1, 0, -2, 1. So basically, all I did was solve the homogeneous system of equations, and I got that. And I said those two, the set that contains those two vectors is the basis. That's what I said right there. Let me close the brackets. That's what I said right there. And the span of these two vectors, the span of those two vectors is the solution space. Vectors in that span, and only vectors in that span, are solutions to AX equals 0. And one last thing I will say is the dimension of the solution space is 2, because the basis only has two vectors. So the dimension, so let me call this W. The basis for the solution space W has those two vectors. If the basis has two vectors, then the dimension of that set, W, is 2. Let's try another two problems. Same type of problem. Find the basis for the solution space W of the homogeneous system 3 times IE minus A, so this is a matrix, times X equaling the 0 vector, where A is the following, where A is equal to -1, 0, -2, -3, 2, 0, -3, 2, 0, and 0, 1, 0. So 3I3, 3 times the 3 by 3 identity matrix, minus A times the vector X. Well, this 3 by 3 identity matrix times that by the number in front gives us this. Multiply all entries in I3 by 3. And then I take away matrix A, -1, -3, 0, 0, 2, 1, -2, 0, 0. And this gets multiplied by vector column vector X, and it equals a 0 vector. Okay. But what is in these big brackets? 3 take away -1 is 4. 0 take away -3 is 3. 0 take away 0 is 0. Even write it more to the left. Get 4, 3, 0. 4, 3, 0. 0, 1, -1, 2, 0, 3. Times X should be the 0 vector. So this is what we want to solve. This is what we want the solution space for. And I put all my energy just to find out what 3I minus A is. It's this. Okay, so I do 4, 3, 0, 0, 1, -1, 2, 0, 3, and I augment it with B, which is all zeros. And I reduce this. And like magic, what I get is this. I get the identity matrix. And if capital X was little x1, little x2, little x3, this implies that x1 is 0, and x2 is 0, and x3 is 0. That is, the solution set only has the trivial solution, has 0. W is equal to that one vector. In fact, the basis for the solution set is that. Now, that's the zero vector. The dimension, since this is linearly dependent, the dimension for W is defined to be 0. The dimension of the zero vector is 0. And I wasn't wrong when I said W is just the zero vector. The dimension of the solution space is 0. Dimension of the zero vector, any space, is 0. Let's do one more problem. Find all real numbers lambda such that the homogeneous system lambda times I2 minus a x equals the zero vector has a non-trivial solution. Has a non-trivial solution for a equal to 2, 7, 3, 1. Actually, let me try a different set of numbers. 2, 6, negative 10, 2. Now, I don't care how complicated that looks. It's a matrix. Call that matrix B. If Bx is equal to 0, has non-trivial solutions, if and only if the determinant of B is 0. Okay? So, I want this to be 0. Well, lambda times I2 is simply lambda times 1. Well, let's write it out. It's lambda times I2 minus a, where a is this value. Lambda times I2 is this. So we want the determinant of this minus a, which is this matrix. And this gives us lambda minus 2, 10, negative 6, lambda plus 2. I want this here equal to 0. This is exactly the equation we're going to solve. So like always, First you multiply those two and you get lambda minus 2 times lambda plus 2 minus this product, which is negative 60. Okay, so what happened? 0, 0, something just isn't working out friendly for us. So let's see what's the problem. Well, I can make it somewhat easier. Let's let A have a negative 6 here. And 0 minus a negative 6 is plus 6. And 6 times 10 is 60. Now, I like to think. This is some number, and this is 4 more. And if I bring the 60 to the other side, the minus 60 to the other side is 60. This number times the number 4 more should be 60. Well, 1 and 60, well, that number is not 4 more than 1. 2 and 30, no, 2 plus 4 is not 60, is not 30. 3 and 20, 4 more than that is not 20. 4 and 15, no. 5 and 12, 6 and 10. That number is 4 more. That is, this can be 6 and that be 10. Or, if this is negative 10, then this number is 4 more. It's negative 6. So, either lambda minus 2 is 6, or lambda minus 2 is 10. If you say, what about lambda plus 2 equaling 10? Well, it's the same as lambda minus 2 equals 6. To convince you, so I claim lambda minus 2 is 6, or lambda minus 2 is negative 10. Well, of course, 8 minus 2 is 6, so lambda is 8. Well, look, if lambda is 8, 8 plus 2, yep, gives me 10. What take away 2 gives you negative 10? Negative 8. Negative 8. And for the record, negative 8 plus 2 is, you got it, negative 6. So here is the answers. If lambda is one of those two numbers, the homogeneous system, this mess equals 0, has a non-trivial solution. We'll have a non-trivial solution when lambda is 8 or negative 8. We will do one more problem. It will be a theoretical exercise. Let S equal x1, x2, up to xn be a set of solutions to a homogeneous system AX equal to 0 vector. And nobody says that this is all the solutions. It's just a set of solutions. Oops. Not a big deal, but the word let did not come out. Now, if this here is all the solutions, S is just inside. Or it can be the whole thing. It's just some, most, all of the solutions. If S is a set of solutions to that homogeneous system, it's going to follow, and we can show that every vector in the span of S is a solution to AX equals 0 vector. What is going on here? We can show that every vector in the span of S is also a solution to AX equals B. Sorry, AX equals 0. Every vector in this set is a solution. Well, how about we take a vector in that set, let V be in the span of S. Well, then that means V is a linear combination of the vectors in S. So V is C1, V1 plus C2, V2 all the way up to Cn, Vn. So here is a vector in the span of S. And every vector, here's an arbitrary vector in the span of S. And every vector in the span of S is a solution to this equation. A times that vector, A times V, that is A times C1 V1 plus C2 V2 all the way up to Cn Vn should be a solution. That is, this should equal 0. Does it equal a 0 vector? That's what we want to find out. But we know that when you have remember, each of these, and I'm underlining on matrices, when you have A times matrix B plus C plus B, even minus, you get AB plus AC plus AB. This is nothing more than A times C1 V1 plus A times this matrix, A times C2 V2, all the way down to A times this matrix. V sub n is a matrix, it's a column vector, it's a matrix, and Cn is a scalar. Now, although a scalar times a vector, or a scalar times a matrix is a matrix, I'm going to think of those C sub i's now as a scalar. And we have a theorem that C times, or scalar times the matrix B, the scalar can come out in front. It's R times CB. So here I have C1 times AV1 plus C2 times AV2 all the way down to C sub n times A times Vn. And this is where it comes together. V1, V2, all the way down to Vn. They're solutions to AX equals 0. That is, AV1 is a 0 vector. This is C1 times AV1, which is a 0 vector, plus C2 times that. The V2 is a solution. Remember, S R is a set of solutions to AX equals 0. This V2 is X. A times V2 is 0. All 0 vector, all the way down to the scalar, the real number Cn times AVn. Well, that's the 0 vector. And we proved this. no matter what. Let's look at C10, 0 vector. That's really circle dot. But we proved that any scalar circle dot the 0 vector is the 0 vector. Again, the 0 vector. The 0 vector over and over again. Well, here it is. When you add up all those 0 vectors, you get this 0 vector. It turned out that A times V is a 0 vector. So yeah, we showed that every vector in the span of S, I took an arbitrary vector in the span of S, and I put it for X. And yeah, A times that vector from the span of S really gave me 0. It really gave me 0. Okay. It's an easy proof if you remember that you can distribute and the scalars can come out in front. And the scalar times the 0 vector is the 0 vector. And this was independent of how we define circle dot. Don't start thinking that scalar multiplication is ordinary. It's not. It doesn't have to be regular. So this completes the section on homogeneous systems.